So in this video, we're going to continue our journey in physical chemistry, and we're going to talk about the idea of intermolecular collisions. So the idea is we want to consider the molecules, right? So consider the molecules of a gas with each having a distance, or each having a diameter d, right? So we're going to call their diameter d. So consider the molecules of a gas each having a diameter d. A collision, we said that a collision is said to occur when the centers of two molecules come within less than the distance d of each other. So a collision, let me repeat that, a collision is actually said to occur when the centers of two molecules come within less than it comes within less than the distance of each other. So let's look at some examples. If we have this molecule, here's a center, and here's a diameter. And we have another molecule, here's a center, here's a diameter. The distance between the center is actually greater than the distance, greater than the diameter. So there's no collision occurring at this point, right? So the distance between centers, right? So the distance between centers is greater than the diameter, right? So greater than the diameter for each molecule, and so essentially this is not a collision. Let's look at another example. We have a molecule like this, and we have a molecule like this. And note my circles are not perfect. Here is D. Here's the center of this molecule. And here is D as well. Well, the distance between centers in this case is actually equal to the diameter of each of the molecule. So in other words, we call this a grazing collision. And then let's look at another example. If we have two molecules, where now here's a center, here's D, here's a center, and here's D. The distance in this case, the distance between centers is actually less than the diameter for the collision, less than the diameters of the molecule, and so in this case we actually have a successful collision, right? So having defined collisions in this way, we actually want to calculate the frequency of collisions between molecules in a gas. So if you want to do that, the first thing we want to do is then freeze the population, right? So in order to achieve our goal of wanting to calculate the frequency of collisions between molecules in a gas, the first thing you want to do is actually freeze the positions of all molecules. So we want to freeze the positions of all molecules except one. Now note that what occurs when one molecule travels through the gas. We want to note what occurs when one molecule travels through the gas. It actually sweeps out a collision tube, right? So if we freeze everything and we have one molecule that's free, it will essentially sweep out a collision tube. All right, so let's look at a collision tube. If I draw a collision tube, right? So this is my collision tube. From this end to that end, we're going to label as the length, but the length we're going to give the average times t. So Vt is the length. Here's our particle, and we're going to say it's actually moving in that direction, right? Here's the diameter of the particle, and we also have a center. Now if we draw, let me actually draw the particle more centered, so excuse me. Let me actually draw the particle more centered. Right? So if this is the particle, there's a center. Here's a diameter d. From the center of the particle, go all the way to the bottom, is also another distance d. And this is the particle that's moving. And then you can see that we may also have other particles within the tube. Again, in the center we have the center, and that's d, but these particles are actually stationary. So this is the idea that we want to freeze all of the molecules except one, which is moving. And we could also draw another particle to show that it's actually stationary. Right? We could draw another particle just outside the tube, right, where we have d, and d is actually greater, so there's no collision. Right? So essentially what I'm saying is that if the particle is directly within the tube, we're essentially going to have a collision because the diameter is less than that of the collision. Whereas if the particle is just on the outside, the diameter is going to be greater, so we're going to have no collision. And so again, this is also a stationary target. So only one molecule is actually moving. So that's the idea that we need to actually calculate the frequency of the collisions. Right? So to kind of explain the diagram, we're saying that a collision tube has a radius d, and we said that the length was v times t. So in other words, we said that the radius of the tube is actually d, and we said that the length of the tube is v times t. The cross-sectional area of the tube is actually sigma, and that is equal to pi d squared. So therefore, if that is the case, then the volume of the tube therefore must be equal to the cross-sectional area times that of the length, right? So therefore, this is equal to sigma times v times t. So that must be the volume, the cross-sectional area times the length. That's what we're saying. Now, sigma, which is the cross-sectional area, sigma, we actually call this the collision cross-section of a gas. So we call this a collision cross-section of the gas. So that's what we define as sigma. Now, some of the typical values that we can actually kind of look these up, but it's nice to give you guys some numbers. And again, this is sigma, so let me actually erase this. It's terrible, right? But you could actually look these numbers up, but it's also nice to kind of have these basic numbers for these basic molecules memorized, right? For methane, it's about 0.46, and C6H6, which is really cyclohexane, or benzene, I'm sorry, it's actually 0.88. So these are some molecules, some species, and the cross-sectional, the collision cross-section, collision cross-section of these different gases. Now the collision frequency is what we actually denote as Z, and it is actually the number of collisions. It is actually a number of collisions a molecule makes per unit time. So it is the number of collisions a molecule makes per unit time. All right, so from the collision tube, we actually see that the number of collisions occurring in the tube is simply the number of molecules whose centers lie in the tube, right? Because remember, we said initially that the stationary target that was just outside the center, that is pretty much not within the center of the tube, there were no collisions, right? So again, from the collision tube, we actually see that the number of collisions occurring in the tube is simply the number of molecules whose centers lie in the tube. So in other words, if we actually let V, or big V, be the volume of the tube of the entire gas sample, or of the entire gas sample, and we actually let N equal, and let me move this up here, we actually let N equal the number of molecules in the sample, then essentially we can actually define a number density. And we actually can define the number density as N over V, right? Simply, again, the number of molecules divided by the volume, and we call that the number density. So if that is the case, therefore, the number of molecules in the collision tube, therefore the number of molecules within the collision tube, is therefore the number density, which is N divided by V, multiplied by sigma times Vt. So this would be the number of molecules in the collision tube. That would be the formula. So if that is the case, then the number of collisions per unit time, or in other words, what we're saying here is the collision frequency must therefore be the number density n over v times sigma multiplied by vt divided by time. Right? And if we simplify that, that is simply equal to sigma times v times n divided by v, or big V. So that would be your collision frequency. But something is missing. We have to remember that the molecules in the tube are not really stationary, right? That's just a concept. So we actually use the average relative speed, right? So because of that fact, we actually have to use the average relative speed. We actually use what we call the average relative speed, and we represent this as VREL. So we use that instead of V because the molecules are not really stationary. Now, this is important because it turns out that the average relative speed is actually equivalent to the square root of 2 times V. And so, if that is the case, in other words, the true collision frequency for a single molecule is therefore in fact Z, right? And that is our collision frequency. Again, and let me write this down a little bit lower. All right. If that is the case, then really what we're saying is that Z is equivalent to the square root of 2 times sigma times V times N, all divided by big V. And so this is the formula that you guys need to know for the collision frequency. Again, the units is in seconds inverse, or in other words, hertz. Now, if we take this a little bit further, we could say then by the ideal gas law, we know that P is equal to nRT divided by V. That is a fact. Where N is the number of moles that can be expressed, right? So N, the number of moles, really can be expressed as number of molecules divided by Avogadro's number. Right? So if that is the case, then our expression of pressure can be different. The expression of pressure can be different, and we could say now P is equal to big N RT divided by NA times V. Okay? Now, if we substitute, or let me write this in a different way, or we could say that this equation is actually P times NA divided by RT, and that is equal to N over V, and this is big N. So now if we substitute for N over V, we actually get Z. Alright, so if we substitute for N over V, we actually get Z to be equal to the square root of 2 times sigma times the average speed, or V, times PNA divided by RT. And this is the formula for the collision frequency with respect to the ideal gas law. Or I could actually write this as Z being equal to the square root of 2 times sigma times V times P over kBt, where kB again is a Boltzmann constant. Again, units in second inverse. So we want to note that the collision frequency is actually proportional to the pressure and inversely proportional to the volume of gas. So this is an important concept. So in other words, as Z increases, the pressure decreases, and vice versa. Right? Well, let me repeat that. So the Z, or the collision frequency, is proportional to the pressure. So as Z increases, the pressure increases, and as Z decreases, the volume increases. So they're inversely related to the volume. And we say it is proportional to the pressure. Now, with that being said, let's try an example. Let's look at an example. So how many collisions does a molecule of nitrogen experience per second at approximately 1 atmospheres and 25 degrees C? Well, notice that we weren't given a volume. And so in this case, we must use the formula without the volume. So in this case, Z is going to be equal to the square root of 2 times sigma times the average speed times PNA divided by RT. And so we have to use this for N2, nitrogen gas. Now we have to use SI units for these problems. Sigma is a volume, is a number we look up, and so for nitrogen is actually 0.43 Newton meter squared. Right, we have to use SI units. So converting this is about 0.43 times 10 to the negative 9 meters, and we square this. And so in SI units, this is equal to about 4.3 times 10 to the negative 19 meters squared. We know that from the kinetic theory, so we know that from the kinetic theory of gases, we know that V, or V average, is equal to 8 RT, and this is from lecture 4, 8 RT, the square root of 8 RT divided by pi m, and if you do the math of this, this is equivalent to about 475 meters per second, right? And this is for nitrogen gas at room temperature. Right? So if we know all those units, then we get our numbers together. So we know that pressure is equivalent to 1 atmospheres, which is equivalent to 1.01325 times 10 to the 5th Pascal. And we know that Avogadro's number is 6.022 times 10 to the 23rd moles per inverse, or moles inverse. We know the ideal gas constant R is equal to 8.314 joules Kelvin inverse mole inverse. And we know that our temperature is about 25 degrees C, which if we calculate that in kelvins, is about 298.15 kelvins. And notice that everything is in SI units. So essentially, if we use our formula for Z, we get the square root of 2 times 4.3 times 10 to the negative 19. And we multiply that by 475. And then we multiply this whole equation, which is, now we plug in our pressure, which is 1.01, 325 times 10 to the 5th Pascal, divided by 8.314 times the temperature, 298.15. And we also have another thing on the top, which is Avogadro's number, 6.022 times 10 to the 23rd. And this is equivalent to about 7.1 times 10 to the 9 seconds inverse. So that would be the collision frequency for a nitrogen molecule at pressure 1 atmospheres and 25 degrees C. Right? So let's finish up the lecture by saying that the average distance of a gas molecule travels between collisions is actually called the mean free path. Right? So this is important. The average distance a gas molecule travels between collisions is actually called the mean free path. And we denote that symbol lambda. So that's the mean free path. So we can calculate this parameter again using the collision frequency. And this is Z in units seconds inverse. And we also need the time between collisions. So if we need the time between collisions, then this is essentially equal to 1 over Z, which the units are going to be seconds. So we just take the inverse of that. So the above two equations represent a general relationship between frequency and time. Right? It's about frequency and time. So in other words, if a baby's heart beats at about 120 beats per minute or 2 beats per second, then the time between the beats must be a half a second. Right? Just taking the inverse. Now the average speed of gas molecule, this is actually equal to V average, right? And the units for that is meters per second. And we know that the distance traveled between the collisions so the distance traveled by molecule between collisions is actually V average times 1 over the collision frequency. Or in other words, lambda is equal to V average divided by Z, and that is equal, and the units for that is actually in meters. Right? So therefore, if we use Z is equal to the square root of 2 times sigma times the average velocity times P, or times Avogadro's number divided by RT, we actually get that the mean free path is equal to RT divided by the square root of 2 sigma times the pressure times Avogadro's number. Let me erase that. So Mm. So we get that is equivalent to RT divided by the square root of 2 times sigma times P times NA, which is Avogadro's number. And this is what we define as a formula for the mean free path. And that is the end of the lecture, ladies and gentlemen.